Hi, in this video, we're going to be finishing our discussion of chapter 14.3 with the discussion of higher order derivatives. In Calc 1 and Calc AB, this would mostly be called like the second derivative and third derivative. Unfortunately, things are no longer that simple. And one very useful technique, especially as we move through this chapter, is going to be a tree diagram. So a tree diagram can come in many different styles, many different shapes, many different forms. For me, let's organize it as starting in the middle of the page. If I have a function of two variables, obviously this could apply for more than two variables. This would be a three-dimensional surface, right? We could take the derivative with respect to x, and we can certainly take the derivative with respect to y. That's the subject of the last two videos. But these two are both functions, as you've seen, that will have two variables, right, inside them most of the time. Sometimes they could have just one, but again, in general, these both still have x's and still have y's. That's why I've been so careful to mention it. That means we can take the derivative with respect to x again of this, and that's a normal kind of thing. If you look at how the Leibniz notation will work out, it's d squared f over dx squared. That's pretty much what you would probably think. You'd probably invent that one if you were trapped in the dungeon, right? You would figure that one out if you had to rediscover this stuff. And our notations are pretty basic. 2x's or z with 2x's. Take the derivative with x, take the derivative with x again. Now maybe that notation itself gives you a hint that instead we could take the derivative of that guy with respect to y. And here's where your troubles begin. Because this notation, the order matters. Sometimes. I have to be a little cagey here. Sometimes the order won't matter. But this means we take the x first, then y. This means we take x first, then y. So what's our notation here going to look like? X first, then y. Right? Think about it like this, okay? Or x first, then y. I'm trying to pause. I'm trying to say it clearly. Notice how these two are backwards. For that reason, we'll usually stick to this. We're not trying to confuse students. However, think about how the operators work if this is confusing you. What happened? Well, it got hit with dx first because these were attaching from the left side. So it got hit with the x first, and then it got hit with the y. Okay? Hit x first, then the y. You got to keep track of it. I'm not trying to sound too cold about this, but that's just how it goes. Likewise, we could take the derivative with this guy with respect to x. And that would look like the same thing, but switched around on just the bottom. Yx or zyx. I'm going to put a line between them just so you don't confuse them. I am not right now saying these two are the same. In fact, I'm trying to tell you that these two can be different. And it's a whole interesting field of study for how and why these two can end up being different things. Okay? So, just pay attention. These two are not necessarily the same. They can be the same, but they're not automatically the same. And going down twice would be taking the derivative of y of your derivative with respect to y. And here it's back to normal. Everybody's happy. Y and then y again. Y and then y again. Okay, so there's like a whole map. And usually that's how I'm going to work this, to be honest. Usually I'm going to do my work in a way where I will organize what the x derivative is, and then I'll take its second derivatives. Or I'll do the y derivative, and then I'll show you its second derivatives. And at the end of the day, if they say find all second order derivatives, you should have 4 derivatives listed. 4 derivatives listed. That's not really a derivative, it's just explaining this notation, right? No time like the present to do examples. Everything will look better in the morning. We have g of xy, x cubed y squared plus xy cubed minus 2x plus 3y plus 1. I'll tell you right now, can you find me dg dx, and we're going to leave some space, and dg dy. We're going to use a more confusing partial notation just to get warmed up, and then I'll probably switch to the other notation forever. I don't know. We'll see. But just try to use this partial notation just so you can see what's going on and get a feel for it. 3, 2, 1. Okay. If you understood the first 2 videos, these 2 should be pretty basic. Certainly easier than implicit. Treating the x stuff as variables, treating the y stuff as constants. I got 3x squared y squared plus y cubed minus 2. This stuff's just constant with respect to x. Okay. And likewise, this guy, normally I would do the other stuff first, but since I just want to make sure we can check your work, should have been 2x cubed y plus 3xy squared plus 3. Because the 2x and the 1 are constants with respect to y. Why did I ask you to leave space? Well, we can go further. Usually this one's a little more natural. We can find the second derivative of g only with respect to x, or with respect to x twice. So that's pretty easy for your brain. At least it is for me. Oh, we're just going to keep doing the same thing. So I'm going to keep thinking the y's are constants. I'm just going to look at the x's, and I would get 6xy squared. This stuff is all constants now because we're thinking of y as a constant. So I'm bringing the power down, subtracting 1 from the power, leaving the y squared, leaving the 3. Okay? The one you got to watch out for is, be very careful, it gets attached on the left side, is what I'm saying. So the notation, the top's going to be the same. We already have our dx, and then we're saying take another y. Okay? Take this guy and differentiate it with respect to y. So now I'm looking at this guy, but I'm focusing on the x's as constants and the y's as variables. Okay. You can try that out yourself, or you can follow along. Here I go. 3, 2, 1. This stuff's now constant. I'm going to bring the y squared down, subtract 1 from the power. I got 6x squared y. This is now relevant. 3y squared. The 2 is a constant. Okay? That's all there is to it. For this one, we're going to find both d squared g, dy squared. And we're going to find, I'll just do it over here, d squared g, dx, dy. Okay, I just want to be really clear how it goes. Try this one first. Just take this with respect to y again. We're slapping another y derivative on it. 3, 2, 1. Did you get 2x cubed plus 6xy? Because that's correct. All right, now, for this one, we're taking this whole expression and we're taking the derivative with respect to x, because we're picturing it like taking a derivative next to it. That's why it gets attached here. So now I'm doing this guy, and I'm focusing on the x's as the variables and the y's as constants. What do you get? 3, 2, 1. X is the variable, y is the constant. Well, I'll just bring the 3 down. Subtract 1 from the power. That's 6x squared y. This guy, x is the variable, turns into a 1 plus 3y squared. And that's all 4 partial derivatives. It is important to be able to find them all. When we go to do things like our test for maxes and mins, you'll need all 4 of them, because it turns out concavity is going to be a lot harder to talk about, or impossible, basically. All right. Let's do another example. fxy equals x sine squared y plus y squared cosine x. And here's the instructions you're going to see. Find all second partial derivatives. Second order sometimes. When they say that, they mean fxx, fxy, fyx, and fyy. We'll use that notation now. Please try this out. It's really not useful if you just sit here and zoom through this example. Here I go. 3, 2, 1. Like I said, start with fx. Sometimes I'll organize my work like this. Treating the y stuff as constant, we get sine squared y and minus y squared sine x. From there, I will sometimes go right over to the second derivative only with respect to x. Now, this is all constant. This stuff's slightly more interesting. I get negative y squared cosine x. Then I'll do fxy. Again, the notation can be confusing. This notation says, hey, you're starting from fx, and now you're adding a y on it. So we're taking this guy's derivative with respect to y. Be careful about something like this. I know a lot of students struggle with this. Make sure you write it as sine y squared if you're the type to get confused. 2 sine y cosine y minus 2y sine x. This is the chain rule and the power rule and the trig rule. This is just the y squared. Sine x is treated like a constant. There you go. 2 derivatives down, 2 derivatives to go. Fy. All right, so now we're in the situation where this guy's the constant, and we have to worry about that power rule sign thing earlier, effectively. So I get 2x sine y cosine y plus 2y cosine x. I'll go right and do fyy. What am I going to get? Fyy is going to be pretty annoying. Why is fyy going to be annoying? Because over here, I need to use the product rule. And despite all the variable mixings we've seen all over the page, this is the only one that requires the product rule. This one. Sorry. This one's the only one that's going to end up requiring a product rule. Spoilers. Why is that? Because I have two functions of y multiplying with each other. Okay, so I'm going to do 2x first times the derivative of the second, negative sine y, plus the second times the derivative of the first, another cosine y. Why did I leave the 2x by itself? Because it's just a constant. Sorry, we're just going to do it over here. We need more room. The 2x is just a constant, and I'm allowed to ignore constants and distribute at the end. Plus, if we're doing another y over here, it's going to be 2 cosine x. Thank goodness that one's easy, huh? Not going to simplify it. You can. This is definitely nice because it's cosine squared minus sine squared, which is a double angle formula for cosine, if you're feeling up to it. All right, now what if I took the derivative with respect to x? So that's this guy with respect to x. That's what that says. You read then, I don't know, this way, it depends on how your perspective is. So, with respect to x, 2 sine y cosine y minus 2y sine x. This is the variable part. The derivative of that is 2. I ignore all that stuff. It's just constants. This is just a constant. The derivative of cosine x is negative sine. Okay, now, for those of you who are observant, you will have noticed that, hey, I thought you said these two weren't always going to match. But on this slide, they matched. What about the last slide? Did our partial derivatives that were mixed match? Yeah. And that's going to be a technical term. It's actually a really important theorem. It's called Clairaut's theorem. I believe that's how you pronounce it. Clairaut's theorem. The name is mentioned in the homework. You don't have to know the name by heart. Of course, you'll sound more cultured if you do. It says, for any function that's continuous on a region. Okay. Don't know why I'm drifting up, but we're going to live with it. The mixed partial derivatives are equal. It's technically if they are continuous. They are also continuous. But in practice, we can use it very abusively. Like, we can just go through it very, very easily. What this is saying is idea as long as the letters match, the order does not matter. For good measure, what am I saying? E.g., fyx is always going to be fxy. But even if we get more crazy stuff, like gxzy is the same as gxyz, is the same as gyxz, but it's not the same as gyxy. That's what I mean by the letters need to match. If we have one of each, you need to have one of each. This guy is the same as gyy, yyx, okay? But there's no linking between them. So in general, the power of this is you can kind of do this in whatever order you want. Whatever order makes the most sense to you. And I'm just going to do a quick example of this, just so you can see. And these are, by the way, these are third order derivatives. They have 1, 2, 3 derivatives. Same here. Just so you know what third order means, it's kind of like the third derivative, or yeah, that's what you would call it in AB. So example, given f of x, y, z, x squared y cubed minus y squared z cubed, find fxyz, fyzx, fzyx, and fxyx. Okay, now you know some of these are going to match if you pay attention to the Clairaut's theorem. But the exercise is to try to make sure you can do this. It's a good test of your abilities right now to verify Clairaut's theorem, so to speak. So the first guy, try it out yourself. I'm going to get started on it now. 3, 2, 1. What's our first derivative? X. I would get 2x y cubed. That's it. Then I want to take the derivative with respect to y. So I'm fixing the x as constant. I'm switching around and going after the y. 6xy squared. And now I take the derivative with respect to z. With respect to z, this whole thing is just a constant. So I get 0. Okay? No big deal. Let's see what fyzx means. So we'll start with y. If you really couldn't do anything, you just watch the video. Try to pause it now. These are not that bad, right? You know what answer you should get for most of them. If I start by focusing my attention on y, I get 3x squared y squared minus 2yz cubed. Then I would go for z. So now this first part fades into the background. It's just constants. 6yz squared. And now I take this guy's derivative with respect to x, because I'm doing this one. Whoops. Yzx. And I would get 0, because with respect to x, this whole thing is constant. Done. 3. Now we're going for this one. Z, then Y, then X. Try it out. 3, 2, 1. Z first. This whole thing is a constant. I'm left with negative 3 y squared z squared. Then y. Negative 6 y z squared. Then x. Well, with respect to x, the whole thing is still a constant. Okay? Notice how these two were the same. So if we already were believing Clairaut's theorem, we know that fyz is going to be the same as fzy. These two were already guaranteed to be the same. Okay? Was fxy the same? No, because these have different letters. But these have the same letters. And that brings me to my final point, fxyx. Now, we already did fx. We already did fxy. But now the directions change and they said do x again. So fxyx is 6y squared. It's not 0. So that's the last wrinkle with these higher order derivatives. In general, if we have a nice continuous function, how do I know that's continuous? It's a polynomial. If we have a nice continuous function, you're not going to worry too much. If it's not a continuous function, we cannot use Clairaut's theorem. Okay? We cannot do it. It will not work out. All right, so that's all we have for this video. In the next lesson, we'll talk about tangent planes and how to use them for a linear approximation. So if you need to review 12.5, now would be a good time. But I'll see you in the next video. Thanks for your attention. Bye for now.